errors today. First of all, cryptography studies about securing the information. It needs mathematically hard problems. So for today's computers, the examples of hard problems for the computers are the famous one, discrete logarithm problem or elliptic curve discrete logarithm problem. But these problems are not hard for the quantum computers. However, there are lattices that provide many hard problems for quantum computers. Lattice is a very similar object to a vector space. We have a basis, and a lattice is all possible linear combinations of the basis with coefficients from the integers. An example of a hard problem based on the lattice is that short vector problem. It is like we are given a basis and we try to find the non-zero shortest vector. And we can think this problem as the closest vector to the origin. Or we can generalize it as like we have a vector that is not on the lattice, and we try to find the closest vector that belongs to the lattice. Another example is learning with errors. So it is the problem that recovering S when we are given samples of this form, that the first entry is n-dimensional vector, and second is a dot product of a vector times the S plus an error. Error, it is like a noise. It distracts you from the information that you have about S and A. Samples of learning with errors are like this. The first is an n-dimensional vector that is over z over Qn. So it is like, the n is the security parameter. So if you increase the n, your security will increase, but the efficiency will decrease. So there must be something optimal. S is the secret. It is important that it shouldn't be found by looking at this sample. So it must be kept secret. E is an integer between 0 and q minus 1. We assume that E must be small. I mean, it can be smaller than this bond, but this bond will be enough for our purposes. Now, one version of the learning with error problem is that search version. Imagine a black box that knows the S, but from outside you don't. So it is just black box. We don't know what is happening inside, but we know that it knows the S. It outputs samples of this form. The first entry is A, so we are given the A, and it takes that product of A and S and adds an error, small error. So A and S is n-dimensional vectors, and error is taken to be small randomly from some polynomial distribution. The problem is finding the S when you have access to this black box. You can take as many samples as you want. The underlying assumption that this problem is hard. Hard means that for any probabilistic polynomial time algorithm, whatever the algorithm is, the probability of this algorithm guessing the S is negligible. It is very small. Another version is decisional learning with error. We can think decisional problems like game. So Alice plays a game with Bob. Alice chooses one of the black boxes that they are identically same from outside, but one of them knows the secret S, one of them does not know. Alice chooses one of them. This one outputs this one the one knowing S. This one does not know S, but the output is similar. So first entry is an n-dimensional vector, and second is integer between 0 and q minus 1. Alice chooses one of them and gives to Bob. The problem is Bob has to guess which box he got, whether the box knowing the S or not. Bob wins if he makes the correct guess. So this assumption is making the correct guess is hard. This means that betting whether the box knows S or not has same probability for any probabilistic polynomial time algorithm. Now, we have the remark that decisional learning with error problem is harder than the search one. This means that if we can solve the search one, then decisional can be solved as well. Because for any probabilistic polynomial time algorithm, we have the following case. Let's assume that search version can be solved. So we have an algorithm that when we give our samples, it can produce S. So we look at the S, and if it fits to be a secret, so if it can be the secret, then we can decide that the box is the one that knows S. Otherwise, we say that box does not know the S. So we can decide after finding S. An example of a learning with of a encryption that uses learning with error problem is that, so in cryptography we have two types of encryption algorithms. One is symmetric. It means that the same key, symmetric key encryption, it means that the same key is used in both encryption and decryption. So the key might differ a little bit, but one of them, encryption key, can be acquired from decryption and vice versa. So here the only requirement is that E must be smaller than Q divided by 4 with high probability. E is taken from some distribution, probabilistic distribution. So the first thing is that we should generate a key, and the input is the security parameter N, and the S is sampled from ZQN. It is uniformly sampled. So it is the secret. We should keep it. It is the key. And the encryption process is that we have S, key, and the message. The encryption is done bitwise, so message can be taught as it is either 0 or 1. The output is the ciphertext. It will be of this form. First, it gives the A as the first entry. In the second entry, we have A dot product, the secret, plus the noise error, and plus mu times ceiling of Q over 2. So mu is either 0 or 1. So we have either last term or not, depending on the message. The ceiling of Q over 2 doesn't matter. We can take the floor or we can take a smaller value as well. It doesn't really matter. Now in the decryption, so we are given a ciphertext. The first is a vector, the second is an integer. So now we look at this norm, B minus A dot product S. So B is this whole thing, and we subtract this, so we are left with this part. Now, if this is less than Q over 4, we say it is 0, because we assume that this is less than Q over 4, and if this is 0, we don't have. We have only this part in here, and if message is 0, we don't have this part, so E must be less than Q over 4. So we decide that mu was 0, so message was 0. The encrypted message was 0, and 1 otherwise. The important thing is that if mu is 1, so this will be a value between 2Q over 4 and 3Q over 4. And if mu is 0, this will be less than Q over 4. So they are non-intersecting cases. So this is why we can decide the encrypted message with high probability. The probability is due to that E is taken to be small with high probability. There is a public key version, which is the asymmetric key encryption. So I can skip this. Now Mohammed will continue. No, Imran.
Okay, I will continue the presentation. So far, Saliha talked about how we use this LWE to do encryption and decryption, and most of the process that we have described is using matrix operation. And in cryptography scheme, there are two things which is very important. The first one is security, and the second one is efficiency. So we want these two things satisfied. It is secure and it is efficient to do. So UBS key Picard and Regev introduced new way to see this vector, this object as a polynomial ring, because in this setting we can convert matrix multiplication and matrix operation that we have seen previous as a polynomial multiplication. Well, in this case we have a better algorithm to do it, which is in the case of matrix operation it is n squared, and in polynomial multiplication it is only n log n based on fast Fourier transformation. So let me describe first how to, what is the idea of fast Fourier transformation is. So we can describe a polynomial in two ways. The first one is coefficient representation. We can represent a polynomial based on the coefficients. And the other way is to describe this polynomial of degree n-1 as n point value pairs, because we can determine uniquely a polynomial using n distinct point. Therefore, we can do this. We can use this two representation of this polynomial. So, using the coefficient representation, if we do straightforward multiplication by expanding the term, then the algorithm is n squared that I said. And in the case of n point value pairs, we can do coordinate-wise or component-wise multiplication on this on the value, so that we have only linear complexity. But the problem is when the polynomial a and b have degree n-1, it means the multiplication will be of degree n to n-2, where we don't have enough points to describe it, but we can still add a more point to describe the multiplication. It only gives you a scalar additional complexity, but we really wanted to describe our polynomial in terms of coefficient representation. So we want to use the idea is to look at first coefficient representation, and then we go to the point value pairs representation, because to do this representation we need to evaluate our polynomial, and it takes also n complexity, linear complexity. So the idea of fast Fourier transformation is to combine these two, but instead of evaluating to arbitrary points, we evaluate the polynomial only on the primitive n root of unity, because we have a nice property of this number. For example, we can evaluate a recursively on the even part of the polynomial and the odd part. So we can always express our polynomial in terms of this. Now the even part and the odd part now is of degree n over 2 minus 1, and we can evaluate instead of evaluate all the primitive n root of unity on a, we can evaluate this now on this the less degree polynomial using our the property of roots of unity, where we can always that the square of n root of unity is describe all the primitive roots of unity of n over 2. That is why we use n should be a power of 2, because we wanted to do this recursively. This is the idea why fast Fourier transformation can be done much faster than the usual multiplication, which takes n log n. Okay, so we can try to adapt this idea to polynomial ring over finite field. Well, in this case, we call it number theoretic transformation. Well, now we want to make sure that the parameter that we choose, which is the power of, this is the cyclotomic polynomial that we use, and the parameter, the degree n, should be the parameter q and n should satisfy this requirement, so that we make sure that there is n root of unity inside our finite field, because we want to adopt the idea of fast Fourier transformation in this case. And instead of, we use the recursive process here. In the case of finite field, we use Chinese remainder theorem recursively, because we can factor our cyclotomic polynomial here, so that in each this is the idea of recursive process that happens when we apply number theoretic transformation. So this is the formal definition of entity and the inverse. It is similar to fast Fourier transformation, but now it is in ZQ. And this is an example how to do it in parallel. So for example, we have an original polynomial, the cubic polynomial, and then we look at the polynomial in the decomposition, which is, we can done it in parallel, and then we do it again by using Chinese remainder again to have this entity of the polynomial. And the way we do the inverse of entity, it is similar to first Fourier transformation, which is interpolation, but we use again the how to say, the process that we have already done from above, from the bigger degree to the less degree. So the idea is to use intermediate multiplier many times. So we use intermediate multiplier in the process. So we don't have to use it a new evaluation again and again. Thank you.